Hello everyone, from Math 1435, it's Pre-Calculus 2. It's Professor Wenson here again with a video on your KnewtonAlta homework, Section 8.2, Part 1, titled Graph Tangent and Cotangent Functions. Okay, so you saw in Section 8.1, we learned how to graph the sine function and the cosine function, right, and variations of those two. Here in this section, 8.2, we're going to do the other four. Alright, so section 8.2 part 1 is on graphing the tangent and the cotangent functions, and section 8.2 part 2, which you'll see later of course, is on graphing the secant and cosecant functions. Alright, so let's get into the tangent and cotangent. Alright, so here I am again, you're not going to see the word preview, but section 8.2 part 1's KnewtonAlta homework. Mastery bar, there are two objectives, right? Click here. There's graph the tangent or cotangent functions over different periods. And the objective on the question I currently have is graph transformations of tangent and cotangent functions. Alright, so it's the first time I'm seeing this objective, so I will go to More Instruction and View Instruction. Now, looks like there's a video here. I am just going to go into, on a piece of paper, I'm going to talk about the graphs of your basic tangent function, y equals the tangent of x, and your basic cotangent function, y equals the cotangent of x, just like I did in the previous section with sine and cosine. Okay, so before we get into the graph of the tangent function, I'll start off with tangent. We have to recall a few things, right? Because I'm going to get into using some special angles to help me plot points on the xy coordinate plane. So hopefully you remember these values for some special angles involving sine and cosine. So remember the sine of 0 radians, or 0 degrees, was 0. The cosine of 0 radians, or 0 degrees, was 1. The sine of pi over 6 radians, or 30 degrees, was a half. The cosine of pi over 6, or 30 degrees, was the square root of 3 divided by 2. The sine and cosine of pi over 4 radians, or 45 degrees, both of them were the square root of 2, then divided by 2, half the square root of 2. The sine of pi over 3 radians, or 60 degrees, was the square root of 3, then divided by 2, or half the square root of 3. The cosine of pi over 3, or 60 degrees, was a half. And then finally, and again, I'm just picking special angles from the first quadrant. If you were drawing these angles in standard position, you'd be going from the positive x-axis through the first quadrant to the positive y-axis. And if you're on the positive y-axis, that's 90 degrees measured out, pi over 2 radians. And finally, the sine of pi over 2 radians, or 90 degrees, was 1. And the cosine of pi over 2, or 90 degrees, was 0. All right, if you got these in mind, hopefully this will help us in graphing tangent and cotangent. I guess I should have put that up as well. Hopefully you recall this from a previous section as well. Remember, the tangent of an angle is equivalent to the sine of that angle divided by the cosine of that angle. Sine divided by cosine. So if we know the sine and cosine of all these values, of all these angles, we can tell what the tangent of these angles will be. Also, the cotangent, and I'll put that down here. Remember, the cotangent was just the reciprocal and one more thing. Remember, the cotangent of an angle, COT, was just the reciprocal of the tangent. So if the tangent of an angle is sine divided by cosine, the cotangent of an angle is the cosine divided by the sine. Alright, so noting all these values, I'm going to make a little table here. Well, not a table, but we can tell you the tangent and cotangent of all these special angles from the first quadrant. Right. So if the sine of 0 is 0 and the cosine of 0 is 1, then the tangent of 0 is 0 divided by 1, or just 0. Right. So the tangent of 0 is 0. And the reciprocal of that would be the cotangent. Now the cotangent of 0 would be 1 divided by 0. Right, it's cosine divided by sine. 1 divided by 0. You can't divide by 0. So the cotangent of 0 is undefined. It has no value. Okay, we're going to start seeing that now. Right, in the previous section, when I was talking about graphing the sine and cosine functions, remember there, the domain was all real numbers. You could take the sine of any angle and get a value. You could take the cosine of any angle and get a value. That is not going to happen here with tangent and cotangent. There are some angles for which the cotangent is nothing, is not defined. And you'll see the same thing with tangent as well later on, right? We'll see it on this page. Okay. Now for pi over 6, or 30 degrees, the sine was a half, cosine was square root of 3 over 2. So the tangent of 30 degrees, or pi over 6 radians, is 1/2, divided by the square root of 3 over 2. Now hopefully you could tell that the 2's would cancel, right? You do a little algebra. That's 1 divided by the square root of 3, right? Or the square root of 3 divided by 3, a third of the square root of 3 if I rationalize. And then flip this over. The cotangent of pi divided by 6, right, of 30 degrees would be the square root of 3. Simple as that. Right. Just flipping over 1 divided by the square root of 3. Alright. This one's probably the nicest one, right? Pi over 4, or radians, or 45 degrees. See, the sine and the cosine of pi over 4 are both the same. So when I divide them, sine divided by cosine, I'm going to get 1. Anything divided by itself is 1. So the tangent of pi over 4, or 45 degrees, is 1. And the same thing would go for the cotangent, right? Just the reciprocal of 1 is 1 again. Right, so the cotangent of pi over 4 is also 1. Right. And for pi over 3, notice for pi over 3, it's just the reverse of pi over 6. Right? Pi over 3, instead of a half, instead of pi over 6, the sine was a half, cosine was square root of 3 over 2. It's the other way around for pi over 3. So just reverse for pi over 3 what you had for pi over 6. So the tangent of pi over 3, right, the tangent of 60 degrees, is the square root of 3. Right, you're going to do square root of 3 over 2 divided by a half. That half will go, and you're just left with the square root of 3. And then the cotangent of pi over 3 is the reciprocal of this, right? Is 1 divided by the square root of 3, or the square root of 3 divided by 3. Sorry about the tightness of that. That's just rationalizing the denominator here. Okay, so again, it's just the reverse. You just switch what you had for pi over 6 for tangent and cotangent. And finally, from this first, again, these are just first quadrant, 0 to 90 degrees. The sine of pi over 2 is 1, cosine of pi over 2 is 0, so the tangent of pi divided by 2 of 90 degrees is 1 divided by 0, sine divided by cosine. Uh-oh again. Right? Uh-oh again. Can't divide by 0. So the tangent of 90 degrees, the tangent of pi over 2 radians, is undefined. It doesn't have a value. But the other way around, the cotangent of pi over 2 would be cosine divided by sine, 0 divided by 1, which is just 0. Okay. So lots of stuff here. I know there's a lot of writing on this page, but I'm going to use this to help me start off graphing the basic tangent function and cotangent function. And so let's start off with, so I'm going to keep the tangent values here. All right, let's keep these tangent values on screen. And we're going to start graphing on the XY coordinate. Now I'm going to make it by hand. I'll show you a better picture on like the desmos.com website. But let's graph, y equals the tangent of x, right, on the xy coordinate plane. Right. So again, I'm doing this by hand here. X-axis horizontal, y-axis vertical. Now, first I'm going to mark off these nice special angles right on the horizontal axis. So we have in our x-axis here, 0, and then I'll go to let's say pi over 2. Right, let's say this is where pi over 2 is right here. Right, so these are all first quadrant angles. Then half of that would be pi over 4. And then you cut this into thirds here. Say here's pi over 6, 30 degrees, and here's pi over 3, 60 degrees, right? Trying to break this into 3 pieces. Alright, and then our outputs, right? Our special outputs were 0, 0, and a third of the square root of 3. Now, a third of the square root of 3, pull the calculator up here. Let's get an approximation for that, so the square root of 3, divided by 3 is 0.577, so a little more than a half, right? And then, the square root of 3 is 1.732. So let's say 0.58 and 1.73 for these special values that are coming up. Right. So we have the square root of 3 divided by 3 as an output for the tangent of pi over 6. Alright, so if I were to say this is 1 unit here, because I know the number 1's also showing up. Alright, the tangent of pi over 4 was 1. So let's say that's 1 unit. And then, like I said, the square root of 3 divided by 3 is about 0.58. So just say a little more than a half, like say here. So there's the square root of 3 divided by 3. And then the other one was the square root of 3 showing up here, square root of 3, which is about 1.72, 1.73. So if that's 1 unit, let's say this is 2 units, and 1.73 is about a little under 1 3/4. Just eyeballing some stuff here. This isn't perfect, but there's the square root of 3. Alright. So now I can plot some points, right, as we did with the sine and cosine functions. Now, the tangent of 0 as we saw here, the tangent of 0 is 0, meaning input 0, output 0. The origin, the point 0, 0, is on this graph here, so I just marked off the origin. The tangent of pi over 6 is, the square root of 3 divided by 3. So I got pi over 6 input, square root of 3 divided by 3 output. There's another point. The tangent of pi over 4 is 1. So input pi over 4, output 1. Tangent of pi over 3 is the square root of 3, right? Square root of 3. So input pi over 3, output square root of 3. And then what do you do for this, right? The tangent of pi over 2 is not defined, right? It has no value. So what I'm going to do on my graph, and you'll see this in your graphs as well, and in the assignment they'll have this for you. The tangent of pi over 2 is undefined. So what I'm going to do is I'm going to put like a dotted line that's not really there to indicate that there shouldn't be any points on this line, right? So this is called an asymptote, a vertical asymptote. You may have heard that word in pre-calculus 1 or some other algebra class you've taken. Right, so here's a vertical, vertical asymptote. And remember, the thing about asymptotes was the graph approached an asymptote, but never became the asymptote. So look at what's trending here. Look at the pattern. Look at what's happening. I start at 0, the tangent's 0. And then as I move toward pi over 2, right, as I move toward 90 degrees, the values of tangent keep going up and up and up and up. So the closer you get to 90 degrees, the larger the output. It's going to be shooting up to infinity, right? Approaching this vertical asymptote. So this part of the graph is going to look, so it looks something like this. It just goes up forever, right? The closer you get to 90 degrees, the higher the value gets. And let me show you. Okay, I'll show you on the calculator. Now I'm going to go to degree mode just to make it a little easier looking. So I'll go to degrees, even though I know my graph is in radians. But if I say, what's the tangent? See, now we already said the tangent of 60 degrees, right, is this, see, that's square root of 3. But then you keep increasing the input. Say, what's the tangent of 70 degrees? Right, you see how it's even larger, 2.74. What's the tangent of 75 degrees? Should be even larger, right? 3.73. The tangent of 80 degrees. Right, the closer I get to 90 degrees, the larger the output gets, right? Tangent of 80 degrees closer to 90 is 5.67. What's the tangent of, I'll go 89 degrees, right, really close to 90. See, it's 57.3. What's the tangent of 89.9999 degrees, right? Really, really close to 90. You see it's huge now. Look at that, 572,957.7951. So you see, the closer I get to 90 degrees, the closer I get to pi over 2 radians. The larger and the output will get as large as I want it to be. If I want it to be larger than 572,957.7951, if I want it to be larger than that, I just go to 89.9999 degrees. Or 99999 degrees, right? Whatever. And again, you'll see on the calculator, if you're using it, the tangent of 90 degrees, or if you're in radian mode, tangent of pi over 2, it's going to come back with an error. See, error, domain. It's undefined at 90 degrees. Okay. So let me get the calculator off screen here. Now this is just a little part. This is just for the first quadrant angles. Now I'm going to do the same for second quadrant angles and and we'll go the opposite direction as well. So 0 to pi over 2 represented, the first quadrant. Do that same distance here. Again, very scientific what I'm doing. 0, I'll just do this with my fingers here. 0 to pi over 2, and then it. Alright, there we go. Alright, so there's pi over 2 to pi radians, right, or 90 degrees to 180 degrees. And then that's our representing our quadrant 2 angles in standard position. And I break this in half and try to break it into thirds. There we go. And there's our, remember our special angles. 90 plus 30 is 120, which was 2 pi over 3 radians, and then 90 plus 45, right, would be 135, which is 3 pi over 4 radians. Then 90 plus 60 is 150, which is 5 pi over 6 radians, right? So our special angle measures, when you're going counterclockwise in standard position in quadrant 2. All right, now if you remember these, if you know these values that I'm pointing to right here on the left, remember the reference angles for these. Now they're in quadrant 2. Now if you hopefully recall, the quadrant 2 angles will have a negative tangent. So I'm going to see all these values again, but negative. All right, so here's -1, and then negative square root of 3 over 3, or negative 0.58-ish. And then -2 and negative square root of 3, about negative 1.73. All right, we'll see all the same values, but negative. All right. Now 2 pi over 3, right, that has a reference angle of pi over 3. And remember, tangent of pi over 3 was square root of 3. So the tangent of 2 pi over 3 is negative square root of 3. Right? I'm in quadrant 2. 3 pi over 4, if you drew that in standard position, has a reference angle of pi over 4. The tangent of pi over 4 was 1, but I'm in quadrant 2, so I'm going to get -1. 5 pi over 6 would have a reference angle of pi over 6. The tangent of pi over 6 is the square root of 3 over 3, but again I'm in quadrant 2, so the output for 5 pi over 6 will be negative square root of 3 over 3. And then the tangent of pi, remember the sine of pi is 0. The cosine of pi would be -1. 0 divided by -1 is 0. So it's kind of like this graph here, this piece of the graph, but going downward, right, looking like this. Okay. And then what you're going to notice is that this graph, what I've just drawn here from 0 to pi, this graph will keep repeating. All right, and I'll show you by drawing some more stuff. And again, you could also use your calculators and try to figure out how this is behaving. Do you see here how if I get closer to 90 degrees, but in quadrant 2, from above 90 degrees, the tangent will be a large negative number, right? Will go down forever. And again, let me show you. Okay, so if I said, again, I'm in degree mode still. So see the tangent of 91 degrees, I should back that up. Should be some bigger negative number, right? See -57. And then if I get closer to 90 degrees, what's the tangent of 90.0001? That's really close to 90 degrees, but above it, it's on the right side of. This should be again a very large negative number. You see that again. All right. And if I wanted to get lower than -572,957, then I just plug in, something even closer to pi over 2, even closer to 90 degrees, 90.0000001, and get something even lower. Right. Okay. All right. All right. So now I'm gonna. So like I said, this is going to keep repeating. And in fact, I'll write that up here. The period. Remember, the period is the smallest positive value for how often the graph will basically repeat itself, right? The period of tangent is not 2 pi like it was for sine and cosine. So be careful with that. It's not 2 pi. The period for tangent is pi radians. This is important. Okay, it changes for tangent and cotangent. Right? Sine and cosine had a period of 2 pi. Sine of x, cosine of x. Tangent and cotangent, you will see, tangent of x, cotangent of x is plane tangent, plane cotangent, will have a period of just simply 1 pi. Right? So yeah, like I said, this picture is just going to repeat over and over again. So from pi over 2 to pi, and then I go from pi over 2 to pi to from pi to 3 pi over 2, right, to talk about third quadrant angles. Cut this in half. That'll be 5 pi over 4, and then try to break it into thirds here. And this is 7 pi over 6 and 4 pi over 3. And we're going to get out the same outputs, and from pi to 3 pi over 2, we're going to get the same outputs that we got from 0 to pi over 2, because all these are just plus pi, right? So 7 pi over 6 tangent has, again, you're in quadrant 3 now. These are quadrant 3 angles. And in quadrant 3, tangent will be positive. And we've seen this. Tangent of 7 pi over 6 is square root of 3 over 3. Tangent of 5 pi over 4 would be 1. Tangent of 4 pi over 3 would be the square root of 3. And then the tangent of 3 pi over 2 will be undefined. So again, a little asymptote, little dotted line here. It's not really there. And it goes up forever, it goes to infinity as you get closer and closer to, this is 270 degrees, right? The closer you get to 270 degrees from below, the larger positive values you're going to get your tangent. And again, I'll show you one more time here. So on the calculator, I'm in degree mode. If I put in the tangent of 269.99 degrees, that's really close to 270, really close to 3 pi over 2 radians. See how it's a really large positive number. Right, it's going to positive infinity on that side of the asymptote. All right, now I could keep going that way forever, but I'm going to also go back to the left. Right, because you notice how between pi over 2 and 3 pi over 2, this graph is nice and connected. It's just this low half plus this top half, nice and connected, nice and smooth, no breaks in it. This is usually what we're going to look at, but over here between pi over 2 and negative pi over 2, so 0 to pi over 2, I'm just going to recreate. Over here there's negative pi over 2, so I'm going to go this way now. Then here's negative pi over 4, then negative pi over 6 for negative 30, and negative pi over 3 for negative 60 degrees. And again, just following this same picture, drawing that same picture over and over again, we will see that the tangent of negative pi over 6 is negative square root of 3 over 3. Tangent of negative pi over 4 is negative 1. Tangent of negative pi over 3 is negative square root of 3. And the tangent of negative pi over 2 is not defined. So again, a nice asymptote right there. All right. Okay, and then it's just this graph again. This graph repeats every pi radians, not 2 pi. It repeats every 2 pi, but it repeats every pi. That's a shorter number, a smaller number for which it repeats. All right, and usually we'll be looking at a graph between two asymptotes, because again, between two asymptotes here, it's very smooth, right? A very nice looking curve. Right? And again, this would continue on and on and on. I'd get this same looking curve every pi radians. So from negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, 3 pi over 2 to 5 pi over 2, negative pi over 2 to negative 3 pi over 2, and so on. Now, off to the side here, I'll put some some neat things, some nice things you should know. The domain of y equals the tangent of x, y equals the tangent of x, is all real numbers except certain ones. Right? There are some values, as you can see, that make the tangent undefined. Right, so the tangent, I can take the tangent of any angle except negative 1 pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. You notice those numbers in front of the pi over 2, negative 1, 1, 3, 5, they're odd. Except odd multiples of pi over 2. Odd multiples of 90 degrees, right? So you can take the tangent of any angle except for odd multiples of pi over 2. The range. What about the range? Well, look at the graph goes, to the down forever, up forever, and there's no gaps, right? There's no spaces in here, so every single y value is used. Every value on the y-axis is a y-coordinate of some point. So the range is all real numbers. You can give me there's an angle that has a tangent of some value no matter what value you pick. You can find an angle with a tangent of 1,000, right? Just get really close to pi over 2. You can find an angle with a tangent of negative 5 million, right? Just get really close to negative pi over 2 here, or really close to pi over 2 on this side. Right. Also, this graph has that origin symmetry. Right? If I take a point, go to the origin, go the same distance across, I'm landing on the graph again. If I reflect through the origin, it's going to give me the same graph. So tangent is an odd function. Remember, that means it has the origin symmetry. Another way to state that would be the tangent of a negative angle, remember, is the opposite of the tangent of the positive angle. This is big here. The tangent of a negative angle is just the opposite of the tangent of the positive angle, as you're seeing in my graph. The tangent of negative pi over 4 is negative 1. The tangent of positive pi over 4 is positive 1. Right? Just opposites. Okay. All right, and I'll show you also a better picture here on the Desmos website. I got desmos.com here. Y equals the tangent of x. Right? You see this repeating over and over and over again, that same kind of curve that I drew. All right. Okay. Now, that was tangent. Now, cotangent is very similar. Very similar. All right. The period will be pi. It'll repeat every pi radians. I'll draw a couple cycles, a couple periods of cotangent. Alright, so this time same thing. I'm going to graph y equals the cotangent of x. Now, this time, I'll draw the first quadrant angles again, from 0 to pi over 2, but this time we're looking at cotangent right here. Remember, the cotangent of 0 is undefined, and then we had all these values here. So I'm going to make again the xy coordinate axes. Then on the horizontal, got 0 here, and then again I'm going from 0 to pi over 2 first. So let's say pi over 2 is here. Cut that in half for pi over 4. Try to cut it into thirds for pi over 6 and pi over 3. And then the special outputs that were showing up were, again, there. Here's 1, and that would be 2 up there. The special outputs were 1, the square root of 3 divided by 3 was a little more than a half, right, about 0.58. And then the square root of 3, almost a little under 1 3/4, 1.73. Now, the cotangent, as we've seen in my previous page, the cotangent of 0, that's undefined. So the y-axis, right, at x equals 0 is one of these vertical asymptotes. So I tried to put a little dotted line over the y-axis there. The cotangent of pi over 6 we saw was the square root of 3. The cotangent of pi over 4 was 1. The cotangent of pi over 3 was the square root of 3 divided by 3, and the cotangent of pi over 2 was 0. And you see it's kind of like the tangent function, but instead of increasing, right, see how the tangent function was going up all the time as you move from left to right, up all the time? This cotangent function is going to be coming down. So you see it's just like the tangent function, on this side of the asymptote it's going to infinity. Right, the closer you get to 0, the closer you get to 0 degrees, 0 radians, the larger the cotangent will be. And you can do 1 divided by tangent on your calculator just to see some examples of that. Alright, so these were first quadrant. And I'm going to go, again, just pi over 2 to pi here, talk about second quadrant angles. So again, cut that in half for 3 pi over 4. Break it into thirds. 2 pi over 3 and 5 pi over 6. And then the outputs, and for second quadrant angles should be negative. Again here, -1. And there's negative square root of 3 over 3. And -2, negative square root of 3. And look at all these negative values. The cotangent of 2 pi over 3, and just following this curve down, it is going to be negative square root of 3 over 3. Cotangent of 3 pi over 4 would be -1. 5 pi over 6 would be negative square root of 3. And then the cotangent of pi, undefined. And you see it following down here like this. And the closer to pi, the closer to 180 degrees, the larger negative value you will get. Right. And like I said for tangent, right, plain old tangent of x, this graph will keep repeating. So once again, like with tangent, the period for the cotangent function is pi. Right? So from 0 to pi looks like this. From pi to 2 pi would look like this. There'd be an asymptote at 2 pi. From 0 to negative pi would look like this. There'd be an asymptote at negative pi. So let me state, I'm just going to draw the 1 period for this. So the domain, right, for cotangent is, I can plug in anything I want. I can put in anything I want for x. It's all real numbers, but with a few exceptions. Right? All real numbers except, now think about this one. 0, pi has an asymptote, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi. So every multiple of pi, every integer multiple of pi, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi, right? So I can take the cotangent of any angle I want except any multiples of pi, right? And when I say multiples, I mean integer multiples of 180 degrees of pi. And then just like tangent, the range is all real numbers. Right? You see it's going up forever, down forever. There's no gaps, no holes. Right. So the range is all real numbers. Now the cotangent, the cotangent is also an odd function. Maybe I should have put another piece of the graph over here. But if I drew another piece of the graph, there'd be here's negative pi over 2, 0, and then coming down like that, and then going up like that, between, to negative pi, and there'd be an asymptote. Go to the origin, go the same distance across. Go to the origin, go the same distance across. Here, go to the origin, go the same. You're on the graph again. Cotangent is also an odd function. So the cotangent of some negative angle is just the opposite of the cotangent of the positive angle. Okay. So you see the cotangent of pi over 3 is square root of 3 over 3. The cotangent of negative pi over 3 would be negative square root of 3 over 3, right? Opposites. So it has that origin symmetry. Okay, so tangent and cotangent are odd. They both have a period of pi. All right, and hopefully now we see how they look, right? They're these nice smooth curves, either falling curves or rising curves between asymptotes, between sets of asymptotes. Now, to the assignment. We're going to be graphing transformations of these, and I'm going to go through and graph them the exact same steps, with the exact same steps that I use to graph sine and cosine functions. All right, exact same steps, that key value method. Now you can read through their instruction here, watch their videos, and if you like what they show you better, do that. But I am going to show you again I'm going to do the exact same steps I did for sine and cosine graphs. The major difference, the major difference is that instead of the period being 2 pi and then getting transformed, that was for sine and cosine, the period was 2 pi and then it got divided by some number. This time, when we're talking tangent and cotangent, the period is pi, and the number pi gets divided by some number, the number times x here. So like this 1/4 times x. Remember how the number times x on the inside of the function, that affected the period? You divided by that number, or the positive version of that number, to get the new period. Instead of dividing 2 pi by that number, you're now dividing pi, just pi, by that number. And that's really the only major difference. All right, let me show you. Okay, so I'm asked, and this is from the assignment, I'm asked to graph y equals 2 times the cotangent of 1/4 x plus pi over 16, all inside, and then minus 2. Now remember how transformations are working. This multiplication by 2 on the outside would cause some sort of vertical stretch by a factor of 2. This minus 2 on the outside will cause a vertical shift down 2, and on the inside, the plus pi over 16 would cause a horizontal shift, and then the x times 1/4 here would cause a horizontal compression or stretch, and that'll change the period. Now, again, I'm going to go through what I called in the previous videos, what I call, and I've seen in other books called the key value method. And if you like the method they show you better, do what they show you. But so remember, first I found that phase shift. I determined the phase shift, and that was taking the expression inside the trig function. Right, so this 1/4 x plus pi over 16, and I set that equal to 0 and solve for x. So this would be x equals negative pi over 4. Negative pi over 4. Right. So this value, I would subtract pi over 16 and multiply by 4. This value right here, negative pi over 4, this is where I'm going to start my graph. I'm going to start the first cycle, the first period of my graph. And if you were asked to describe the phase shift, that having this be a negative, this would be the phase shift would be pi over 4 units, and because it's negative, left. Right? Negative values are to the left on the horizontal axis. All right, so I'll start the first cycle there. Again, hopefully this is all looking familiar to what I did in the sine and cosine videos. Next, I'm going to determine the period, right? How long is this one cycle I'm trying to draw? All right, so the period is now, when it was sine and cosine, I had a numerator of 2 pi. But for tangent and cotangent, the numerator will be pi, right? Because again, this is pi since we're talking cotangent. All right, it is a cotangent function. All right. Tangent and cotangent have a period of pi normally. Right? And then this gets divided by the number times the x, right? Remember that number, the positive, if this is a negative number, make it positive, because your period should be a positive value. So divided by 1/4. All right, so pi divided by 1/4 is the same thing as pi times 4. So the period is 4 pi. All right, the period is 4 pi. So from the beginning of my first cycle to the end of my first cycle should be a distance of 4 pi radians. So I'm going to determine, so the end of my first cycle, right, the end of my first cycle will be at x equals, I'll take where I'm beginning it, negative pi over 4, and I'm going to add, the period, add 4 pi. And that'd be at 15 pi over 4, right? You got to get the common denominator. All right, that's negative pi over 4 plus this is 16 pi over 4. So that gives me 15 pi over 4. All right, so I'm going to start at my first cycle. I'm going to start my chart at negative pi over 4 and end it at 15 pi over 4. Now comes the most, probably, I feel the most important part of this, is the distance between these key values that I'm talking about, where I take the period, the 4 pi, and I break it into quarters, right? So I determine what's a quarter of the period. So this is a quarter of 4 pi, right? The period I found earlier. That's just pi, and I'm going to put this in a nice little bubble. This is huge, right? This pi, this is going to be the distance between each of my key values on the x-axis. So the distance between what I'm calling key values on the x-axis. All right, then I make a little table. So we have x values, y values, And the first, again, a table of these key values right here. Right. The first of these is, like I said, when I found that phase shift, where am I starting? It's at negative pi over 4. Negative pi over 4 is where I'll start my graph from. Right, then I'm going to keep adding pi, right, this quarter period. I'm going to keep adding pi to get more and more of these key values until I get to the end of my first cycle, until I get to 15 pi over 4. So negative pi over 4, plus pi. Remember, pi is 4 pi over 4. So add pi, you'd have 3 pi over 4. Add pi again. Maybe I should write this, what I'm doing here. This is, I'm adding pi, right, that quarter period. Add pi again to get 7 pi over 4. Add pi again, get 11 pi over 4. And then I add pi again, and there's your 15 pi over 4, right, where I said the first cycle I'm drawing is going to end. Now, if you're doing this right, there should be 5 of these, right? You saw this in my previous videos on graphing sines and cosines. For this first cycle, right, this first period, there were 5 of these key values, right? Because I was breaking it into quarters. Right? You break a thing into quarters, there should be 5 markers, five points. Okay. Then I just plug these into the function. Right, there's the function here. I plug in and plot points. So plug in these key values and graph. And hopefully, again, now for this first example, I'll take it slow. I'll actually show you what I'm getting here when I plug in these key values. Now again, the whole reason I'm calling these key values is because when I plug them in, you're going to see the angle inside the cotangent. It's going to be something really nice. It's going to be some multiple of pi over 4, which hopefully knowing you'll know the cotangent of really easily. So I'll start off with x equals negative pi over 4. Pi over 4. That's pi there, sorry. Well, if I plug in pi over 4, or sorry, negative pi over 4 for x, right? We said that would make this 0. I'd have 2 times the cotangent of 0, and then minus 2. Now we said it a second ago, right? I had here is that cotangent graph one more time. Remember, the cotangent of 0 is undefined. This is undefined. So I'm going to put that in my chart. UND for undefined. Now all that tells me is that I'm going to be putting an asymptote at negative pi over 4. Okay. Alright, the next key value. X equals 3 pi over 4. We have y equals 2 times the cotangent of. Now when I plug in 3 pi over 4 for x, a fourth of that would be 3 pi over 16 plus pi over 16 inside here would be 4 pi over 16, which is reduced to pi over 4. And then you have the times 2 minus 2. Now, the cotangent of pi over 4 we saw was 1. So I'm getting a value of 0 here, right? The cotangent of pi over 4 is 1, and then I times 2 minus 2, get a value of 0. Okay. Alright, then I'll plug in 7 pi over 4 for x. X equals 7 pi over 4. Now when I do that, a quarter of 7 pi over 4 is 7 pi over 16. Plus pi over 16 would be 8 pi over 16, which reduces to pi over 2. So I have y equals 2 times the cotangent of pi over 2. and then minus 2. Now, again, we saw this earlier. The cotangent of pi over 2 is 0. All right, cotangent of 90 degrees. So this is 2 times 0 minus 2. That's just negative 2. So you got an output of negative 2 here. All right. The next one, x equals 11 pi over 4. And plug that in for x. Now, a quarter of 11 pi over 4 would be 11 pi over 16. Plus pi over 16 would be 12 pi over 16. And 12 pi over 16 reduces to 3 pi over 4. So we have 2 times the cotangent of 3 pi over 4, then minus 2. And again, we saw this on my graph earlier. The cotangent of 3 pi over 4 is negative 1. And 2 times negative 1 is negative 2, minus 2 is negative 4. And then if I did this correctly, the end of the chart should be the same as the beginning of the chart, because we said, remember, the period is 4 pi. So any x values that are 4 pi apart should have the same output. And negative pi over 4 to 15 pi over 4, these are 4 pi apart. So it should be undefined. I'll plug it in and show you. We'll have another asymptote here at 15 pi over 4. But I'll plug it in and show you. Right? When I plug in 15 pi over 4 for x, right, we got a quarter. A quarter of 15 pi over 4 would be 15 pi over 16. Plus pi over 16 would be 16 pi over 16, which is pi. Right? So y equals 2 times the cotangent of pi, and then minus 2 again. Saw earlier, right? Remember, the cotangent is undefined at integer multiples of pi, right? So 0, 1 pi, 2 pi, 3 pi. So this is therefore undefined, has no value. Okay, which I said in my chart. Right. Now, I'll take this chart for one cycle here and start graphing. I'll make a hand drawing. Right, so I'll keep the chart up there. All right, so I'm going to draw x-axis, y-axis. On the x-axis, I'll mark these values off. Again, I'm going to try my best to make these look good. So if this is let's say this is negative pi over 4, right, where I'm starting. That's a quarter of pi. And then I'll take like 4 of these, one little fingertip widths. 1, 2, 3, 4. Let's say there. That's the next one. This might not be great, but 3 pi over 4. Right, and then I'll just keep adding this. There's 7 pi over 4. And then just eyeballing this now. And there's 11 pi over 4. And then the same distance again, 15 pi over 4. Again, it's a hand drawing, not the greatest, but I'm trying to make sure all these notches are pi apart, right? I kept adding that pi, that quarter period. Now I said here the value of this function is undefined at negative pi over 4. So vertical asymptote. It's also undefined at 15 pi over 4. Vertical asymptote. And then the values at these other inputs are 0, negative 2, let's say that's negative 1 there, and then negative 4. So plotting points, 3 pi over 4, 0. 7 pi over 4, negative 2. 11 pi over 4, negative 4. And this should be enough, knowing what we know about these cotangents and tangents. Remember, cotangents and tangents are these smooth curves between asymptotes. They go up forever and down forever at some point. Now they could be falling curves, they could be rising curves. It all depends on what number is in front of the cotangent. Now notice there was a positive number in front of the cotangent. So that means it's not going to flip. It'll just still be a falling curve, right? So something like this. That's in the middle there, and then it keeps falling. So something like that. Right? Not the best looking picture in the world, but a rough idea, pretty good rough sketch of how the cotangent, this particular cotangent function we were given, will look. All right. So what are you doing on the assignment? On the assignment, you're going to be, it's one of those interactive deals where you're moving stuff around. Now it says, drag the movable black point to set the left vertical asymptote and shift the function. The red point to set the right vertical asymptote, thereby setting the period, right, how long one cycle is. And the blue point to correspond to the correct set of coordinates, right? You may click on a point to verify its coordinates, and it says, note that the two asymptotes can be moved independently of each other, and that only one period, one cycle of the thing is shown. All right, now I said that the left one, in my picture, I put the left one at negative pi over 4. All right, so there's negative pi over 4 is 0. The right one I set at 15 pi over 4, which is just below 4 pi. Right there. See, there's 15 pi over 4 for the x value. So my asymptotes are 4 pi apart, and then it looks like I'm just moving a couple of these blue points around. Now one of them's at the middle, and one of them's, there's only two of them. See how one of them's at the middle where it turns? Right, it goes from being curving up to curving down. So that point on my graph, right, here is my picture again. That point on my graph was 7 pi over 4, negative 2. So on this, I'm moving this 7 pi over 4, which is already at, but just down to negative 2. Oh, it looks like the only one I can move is this one. Alright, so keep the middle there, I guess, and let's see, this point is at 3 pi over, yeah, so 3 pi over 4. But my one at 3 pi over 4 had an output of 0. So I'll move this 3 pi over 4 comma 1 down to 3 pi over 4 comma 0. And then why can't I move this point? And the blue point to the correct set of coordinates. Well, I can't move this one. Why not? Alright, I'm going to pause this for a second and try to figure this out. Okay, so it looks like you have to drag the black point up and down the asymptote to move the middle. So I dragged the black point here down, from to negative pi over 4 comma negative 2. That moved this middle point to where I wanted, right? The 7 pi over 4 negative 2 on my graph. And then I want 3 pi over 4 negative 1 to be at 3 pi over 4 comma 0, like in my picture, 3 pi over 4 comma 0. And then the middle here where it turns, changes from curving up to curving down, that middle point to be at 7 pi over 4 negative 2 there. So you got to drag the black point up and down the asymptote to move the middle, it looks like. And I submit. Looks great. Yeah, so notice again I used the same steps, the same 5 steps that I went through for the key value method when I graphed sines and cosines. Alright, just got to remember how these tangents and cotangents look, right? They're these nice smooth curves going up forever, down forever between pairs of asymptotes. Yeah, and the main thing to remember is that your period for tangent and cotangent, normally cotangent x, tangent x is pi, not 2 pi. And that's going to be key. Okay. So let's do another one like that. Looks like it's another cotangent. Right, they might throw some tangents at you. So I'm going to do the same thing, but a little faster, right, on a piece of paper. All right. So here's that cotangent, another cotangent function we're given. And I start off, I'm going to take 4x plus pi, set that equal to 0. That's x equals, negative pi over 4. All right, so this is where I'm going to start my first cycle. All right. Then the period. Again, this is a cotangent function. Cotangent. If it's tangent or cotangent, to find the period of the new transform function, you're going to take pi, not 2 pi. You're going to take pi and divide it by the absolute value of the number that's multiplied by the x inside, right? X is multiplied by 4 here. So the new period is pi divided by 4, meaning I'm going to end my first cycle at negative pi over 4, right, where I'm starting, and then I add pi over 4. That's 0. All right, so I'm going to start my chart at x equals negative pi over 4 and end the chart at x equals 0. All right, then I'll take break this into quarters. What's a quarter of the period? That'd be pi over 16. All right, pi over 16, a quarter of pi over 4. So the distance between all my notches on the x-axis, the distance between each of these key values that I'm setting up, is pi over 16. And then I'll make a little chart, a little table. We're again starting the first cycle here at negative pi over 4. And then I just keep adding pi over 16. Now get a common denominator, right? This is negative 4 pi over 16. So if I add pi over 16, it'll be negative 3 pi over 16 for the next key value. Then negative 2 pi over 16, which is negative pi over 8 when you reduce it. Then negative 1 pi over 16. And then adding pi over 16 one more time, see I'm ending at 0. This is the length of one period, one cycle, right? The distance from the beginning here to the end, negative pi over 4 to 0, is pi over 4 radians. And then what I draw here should just repeat over and over and over again. Right? I would just keep repeating it if I wanted to draw more cycles. All right, so now I plug these values in. Now we already knew, when I plug in negative pi over 4, you're getting the cotangent of 0, which is undefined. So I'm going to have an asymptote here at negative pi over 4. When I plug in negative 3 pi over 16, well, that'd be negative 3 pi over 4, right? This times 4 would be negative 3 pi over 4 plus pi would be just pi over 4. And the cotangent of pi over 4 is 1, times 3 is 3, minus 1 is 2. Right, so again, output a 2 when I plug that value in. Negative pi over 8. 4 times that would be negative pi over 2, plus pi would be positive pi over 2. The cotangent of pi over 2 is 0. 0 times 3 minus 1 be negative 1. Plugging in negative pi over 16, 4 times that would be negative pi over 4, plus pi would be 3 pi over 4. The cotangent of 3 pi over 4 is negative 1 times 3 is negative 3 minus 1 is negative 4. I mean, you should really eventually get to the point where you're that quick. All right, and then undefined here. All right, again, if you did things correctly, if this truly is the period of the function, and these are pi over 4 apart, then they should have the same output, basically have no value, be undefined. All right, then I'll draw a rough sketch of what this cotangent function will look like. All right, so x-axis, y-axis, and let's say negative pi over 4 is over here. All right, and then I'm cutting this into quarters, right? And then here's 0 at the end. And then just break this into quarters. Here's the negative 3 pi over 16. Here's the negative pi over 8. Here's the negative pi over 16, right? And set it up. Try to draw it. I'm trying to draw it here so that all my notches are the same distance apart. Now we have an asymptote here at negative pi over 4, have an asymptote here at 0, and then all these outputs are at, 2 and negative 1 and negative 4. Plot these points. And again, this is a cotangent function. You should hopefully know what the tangent and cotangent functions look like. Now, the cotangent function normally is a falling curve, and this is being multiplied by a positive number, so that's not going to change, right? If it's multiplied by a negative number on the outside, then it'll flip and be a rising curve between asymptotes. But cotangent is normally a falling curve between asymptotes, and it's multiplied by a positive number, so that will not change. And it's curving up, and then in the middle, at that middle point here, it changes the curve. It curves down. Right. So there's one cycle. All right. So again, I'm going to be moving stuff around on the website on the assignment so that this picture shows up. This one cycle. All right. So I started off my first asymptote here at negative pi over 4, which is here. Right? Negative pi over 4 comma 0. Now remember, I got to move this so that the middle point doesn't have an output of 0. I want to have an output of negative 1. Right? I'll pull my picture up on the right side here. See, this is at negative 1 for the middle point. So I'm going to move that black dot down to be negative 1 there. The right asymptote is at 0. Right? So it's going to be really tight. Right there. Okay. And again, see how the middle point now, this middle point that I can't move, is at negative pi over 8, negative 1, exactly where my point is, negative pi over 8, negative 1 in the middle here. And then this point up top here that I can actually move, I want it to be at negative 3 pi over 16, comma 2. Right? So I'll move this up to 2 there, and see that's negative 3 pi over 16, comma 2. So there's one cycle, this falling curve between these two asymptotes, like I have in my drawing, only it's a lot thinner on their drawing here. Wonderful. Yeah, so you should be able to draw at least one cycle. Now, again, this picture that's drawn here, from 0 to pi over 4 would repeat, and then from pi over 4 to pi over 2 would repeat. Right? It would repeat every pi over 4 radians, right? Every period. All right, here we have a tangent. All right, I'm going to do the same thing. All right, notice it's the same kind of stuff where you have to move pieces of graph around. All right, so I'm just going to do this one more, and then I'll call it, because that's all you're doing for all these problems. It looks like is graphing one cycle, one period of these functions. All right, so I'm going to pull this up on paper again and graph this tangent. And then I'll just stop, because again, that's all you're doing. This entire section is tangents and cotangents. This entire assignment, section 8.2, part 1. All right, so same stuff. The expression inside, when is 5x equal to 0? This isn't nearly as complicated as the last couple examples. That's when x equals 0. All right, so this is where I'm going to start the first cycle of my drawing. All right. Then the period of this new function, this tangent function. Again, it is a tangent function. Pay attention. If it were sine or cosine, I'd take 2 pi and then divide it by 5. But it is tangent. If it's tangent or cotangent, you take pi. Right? The period for tangent and cotangent, the original cotangent and tangent is just pi. And then this is getting divided by 5 here. All right, so the period's pi over 5. So I'm going to end the first cycle at x equals pi over 5. All right, because it's just 0 plus pi over 5. All right, then what's a quarter of this? All right, break it up into quarters for these key values I like. Well, that'd be pi over 20. Right, so this is going to be the distance between each of my notches. All right, pi over 20. And then I'll make a little table. Starting at 0, and then I just keep adding pi over 20. So pi over 20, 2 pi over 20, which is pi over 10, 3 pi over 20, and then 4 pi over 20, which is pi over 5. And 0 to pi over 5, that's a whole period. Right? That's one full cycle. All right, now this time I'm doing the tangent values. Right here was the graph of my tangent. Now remember, tangent is normally a rising curve. It's curving down, then curving up. It's a rising curve between asymptotes. And see here, it's still times 1 times a positive number. So when I graph this new tangent, it'll be a rising curve between asymptotes. If it was multiplied by a negative number, it would flip that and be a falling curve between asymptotes. And just remember how, remember all the values that came up earlier in the video, right, where there are asymptotes and stuff like that. Alright, so I plug in these values. Plug in 0, you get tangent of 0. The tangent of 0 was 0. So the point 0, 0 is going to be on this. I plug in pi over 20. 5 times pi over 20 would be pi over 4. The tangent of pi over 4 is 1. Plug in pi over 10. 5 pi over 10 is pi over 2. The tangent of pi over 2, remember the tangent of those odd multiples of pi over 2 were undefined. So there's going to be an asymptote at pi over 10. Plug in 3 pi over 20, that'd be 3 pi over 4. The tangent of 3 pi over 4 is negative 1. And plugging in pi over 5, you get the tangent of pi, and the tangent of pi should be the same, again, the same as the tangent of 0. The beginning and end of my cycle here should have the same outputs if the period truly is pi over 5, and it is. And then I'll start plotting this first cycle, and we might have to continue it to make it look a little nicer. And here's so again, let's say here's 0, and let's put pi over 5 here, and I break this into quarters. Everything's evenly spaced. And here's pi over 20, here's pi over 10, here's 3 pi over 20. All right. I said there'd be an asymptote at pi over 10. Right? This function is undefined, has no value at pi over 10. All right, and then the outputs that show up here are 0, 1, and negative 1. And let's plot them. All right, so we got 0, 0, pi over 20, comma 1, 3 pi over 20, comma negative 1, and then pi over 5, 0. And remember how that graph of the first tangent, it's that curve, but it's broken up, right? You got the top half of it here, and then the bottom half of it over here. Remember that first graph of tangent I made. Now this isn't like what they have in the website. This isn't like what they have in the assignment. They want you to graph one cycle of this curve between two asymptotes. All right, where the center is at 0 and stuff. So I'm going to keep drawing more on this. Right? So this is one cycle. Now keep this in mind. Right? I'm just going to keep this pi over 20, right, that I had here, this quarter period. I'm just going to keep adding and subtracting this, and we'll get more special values, more key values. So if I keep going, let's say go this way. So 0, and then I subtract pi over 20. So here's it should be the same. Again, I'm trying to keep everything the same distance apart. Negative pi over 20. Then another one, negative 2 pi over 20. Then another one, negative 3 pi over 20. Then another one, negative 4 pi over 20 would be negative pi over 5. Here's another period, right? 0 to pi over 5, that's pi over 5, the period, right? 0 to negative pi over 5 is another pi over 5. So I should get the same exact picture from 0 to pi over 5 as I will from 0 to negative pi over 5. All right, so if I get the same exact picture, that means there'll be an asymptote at negative pi over 10. The output at negative pi over 20 will be negative 1, right? Because that's pi over 5 away. The output at 3 pi over 20 will be positive 1. And the output at negative pi over 5 would be 0. Again, I'm just drawing that same picture again here. You got top half to the left of the asymptote, bottom half to the right of the asymptote, and there. And there's two cycles. Here's two cycles of this tangent graph. Y equals the tangent of 5x. And we're asked to graph this part here. Right? This is in the assignment. Right? You're asked to give them a graph of one cycle of this tangent function, between two asymptotes. All right, so I go back here. Again, I'll pull up here's my picture. Now, we're asked to move the asymptotes, right? So remember, this is from negative pi over 5 to pi over 5. So the left asymptote's at negative pi over 5. And see, this is one where it moves both of them. So you see I got negative pi over 5 to pi over 5. The middle's at 0, 0, looks like. Just asking us to move this top point, which is at pi over 20, comma 1, which I think it's already there. Click on it. Oh, that's at pi over 10, comma 1. Oh, nope. Sorry. Not negative pi over. These are the asymptotes. My apologies. The asymptotes are at negative pi over 10 and pi over 10. You see the dotted lines on my picture. My bad. So I gotta move these a couple more in. There we go. So there we go, negative pi over 10. So now the asymptotes are at negative pi over 10 and positive pi over 10. And this point here is at pi over 20, comma 1, which is what I have in my drawing, pi over 20, comma 1. And it's a rising curve between asymptotes. Looks perfect. Okay. So yeah, so again, I'm doing the same steps every single time. You just have to remember that for tangent and cotangent, to get the new period, you're going to be dividing pi by something instead of 2 pi. I think I've said that enough by now. All right, and like I said, I believe every single problem is like this. Yes, it is. All right. So this one you have 2 times that. So all that would change, you'd have the same asymptotes. I'm telling you, negative pi over 10 to pi over 10, but instead of pi over 20, comma 1, you'd have pi over 20, comma 2, because of this multiplied by 2 out front. Because the inside of the function was still the same, 5x, so it was kind of a joke one. And you can do it by hand. I would recommend trying to do it by hand first. All right, this one's similar. I'll say I know where they're going to be, right? Instead of the period's going to be pi over 2, right? Period's going to be pi over 2, so these asymptotes will be from negative pi over 4 to pi over 4. Then then you have instead of pi over 8, comma 1, it'll be pi over 8, comma 4 because of the times 4 there, right? And it's going to be still rising because it's a tangent rising between asymptotes, and you're multiplying by a positive number. That won't change. You got one more like this. Now this one's a cotangent. Careful, cotangent, remember, is they got the falling functions, falling between asymptotes. And you're multiplying by a positive, so again, that's not changing. It's still going to be a falling curve between asymptotes. And normally, remember, period's pi, it's from 0 to 2 pi, 0 to pi, those asymptotes. But this is going to be period of pi over 2, so from 0 to pi over 2. And 0 to pi over 2 will be the asymptotes. And then, instead of this point here being at pi over 8, comma 1, it's going to be a pi over 8, comma 2. Right? Again, I would recommend drawing it by hand first, right? I mean, I've done this a million times, so that's why I'm able to fly through these. But I would recommend drawing it by hand first. I like following those steps. Okay, and then here, right, another tangent. All right, I'll draw this. I'll do this one again pretty quick on a piece of paper, and a little more complicated. All right, so the first thing, I'm going to start my cycle at x equal, wherever this inside here is equal to 0. Solve for x here. That'd be negative 2 pi over 12 or negative pi over 6, right? If you were to, again, set this expression inside equal to 0, you have to subtract 2 pi over 3 and then divide by 4. The period of this function will be pi, again, it's tangent, so I'm taking pi, not 2 pi, and dividing by the number times the x, the positive number, and it's positive 4. If it were negative 4, you'd still divide by positive 4, right? So the period's pi over 4. So I'm going to end the first cycle I draw at negative pi over 6, right, where I started, plus pi over 4, right, plus 1 period. And getting a common denominator, this is negative 2 pi over 12 plus 3 pi over 12. That'd be a 1 pi over 12. Right. Yeah, so these are 3 pi over 12 or pi over 4 apart. And then what's that distance between each of my notches? The distance between each key value. A quarter of the period would be pi over 16. All right, so this is going to be the number I add and subtract to get to the different key values. All right, and then I plug them in. I'll do a little chart here for one cycle. So starting at negative pi over 6. Starting at negative pi over 6, and I'm going to keep adding pi over 16. Now you get a common denominator here. Pi over 6, pi over 16. That's 2 times 3. That's 2 to the 4th. So 2 to the 4th times 3. That's 48. So this would be a 3 pi over 48. And this is negative 8 pi over 48. Right. So there's negative 8 pi over 48. And I just keep adding 3 pi over 48. Right. So negative 5 pi over 48. Then negative 2 pi over 48, which would be negative pi over 24 for the middle there. And again, that's negative 2 pi over 48, and plus 3 would be pi over 48. And then finally 4 pi over 48, which is pi over 12, which is what I said I would end at. So here's one cycle. And then plugging these values in for into the tangent function here give me some nice outputs. When I plug in negative pi over 6, I get the tangent of 0. Well, the tangent of 0 is 0. Times 2 minus 1 would be negative 1. Plugging this in, again, you can simplify if you wish, but you're going to get the tangent of pi over 4. Because it'd be negative 5 pi over 12 plus it'd be negative 5 pi over 12 plus then 8 pi over 12 would be 3 pi over 12 is just pi over 4. The tangent of pi over 4 is 1 times 2 minus 1 would be positive 1. Here you plug this in, you're going to get the tangent of pi over 2, which is undefined. So I have an asymptote at negative pi over 24. And then plugging this in will give me the tangent of 3 pi over 4. Go ahead and simplify that. The tangent of 3 pi over 4 is negative 1. So then times 2 minus 1 is negative 3. And then again, if I did everything correctly, the output at the end of the chart, the table there, should be the same as at the beginning. All right. Now I'll plot these points, and we'll also work with some other values, because they want us to graph things between two asymptotes. So again, starting here at negative pi over 6. Let's see, that's here, right? So negative pi over 6. And then that was a bad start. Okay. Eep. Alright, let's do this again. Alright, so I'm starting at negative pi over 6, which is negative 8 pi over 48. Alright. So let's say each of these notches, I'm gonna make really tiny ones. There's 1, 2, 3, 4, 5, 6, 7, 8. Let's say these tiny notches are every pi over 48. Alright, so here's negative 8 pi over 48 or negative pi over 6. And then I just keep adding 3 of these. So 1, 2, 3. There's negative 5 pi over 48. And 1, 2, 3. Here's negative 2 pi over 48 or negative pi over 24. And 1, 2, 3. There's positive pi over 48. And then 1, 2, 3. And then pi over 12. All right, again, trying to get these the key values of the big ones, right? The big ones are all the same distance apart. Wonderful. We said there'd be an asymptote at negative pi over 24 here. And then the outputs that are showing up are, 1, negative 1, and negative 3. So let's say this is 1 here, then negative 1 here, and then negative 2, negative 3. And plotting some points. Negative pi over 6, negative 1. Negative 5 pi over 48, positive 1. Pi over 48, negative 3. And pi over 12, negative 1. Again, notice that the tangent was multiplied by a positive number on the outside, so it's going to be just like my tangent earlier where it's rising here and rising here. It's rising the whole time as you move from left to right. Now, as I said before, they don't want this picture. Right, that is one cycle, but they want one cycle that's between asymptotes here. All right. They want a cycle between some asymptotes. So let me go back here and let's just keep taking this quarter period, right? This distance between key values, and let's go in another direction. Let's see. I mean, I could go either way. Let's go this way. So 1, 2, 3. There's now this was this is 3 pi. Oh, sorry, 4 pi over 48. So this would be 7 pi over 48 here for the next key value. And then 10 pi over 40. I just keep adding this pi over 16. Now 10 pi over 48. That's 5 pi over 24. All right. And just following the pattern here, see at 7 pi over 48 should have a value of 1 when I plug it in. And then at 5 pi over 24, that's 6 pi over 24. That's pi over 4 away from the other asymptote. Remember the period's pi over 4, so all the asymptotes should be pi over 4 apart here. Got another asymptote at 5 pi over 24. And here's a cycle that's between two asymptotes right here. All right, so this is what I'll draw right here, right, between the two asymptotes. This is what I'll try to draw in the assignment. All right, so back to the websites here. I'll pull my picture up. All right, now they're saying here, drag the movable black point to shift the function, the red points to set the asymptotes, the blue point at the correct set of coordinates. Okay. So, looks like this. All right, the middle point is at pi over 12, negative 1. Okay, I gotta move the asymptotes first, it looks like. All right, so negative pi over 24. Doesn't look very good. Negative pi over 8. Positive pi over 8. Alright, I guess I gotta shift the middle a bit. Shift it to pi over 12. Why doesn't that move to pi over 12? Alright, I'll be right back when I figure this out. Alright, so it looks like the only way I could have gotten it to have one of these asymptotes at negative pi over 24 was I moved the black dot to the middle over here. This negative pi over 6 comma negative 1 right there would be the middle of the curve over here. And then you'd have an asymptote at negative pi over 24 and then negative 7 pi over 24, which is, pi over 4 apart. So that seems like the only way I could have done it. And then I moved this other point here up to so that it has an output of 1, the blue point. So it has an output of 1. Now notice it doesn't come back with negative 5 pi over 48. It's negative 3.327, but it has an output of 1. So yeah, it looked like I had to move this left in order to get the asymptotes to line up. All right. Still, I guess I moved the middle point. I moved that middle point first, and then shifted the asymptotes. Right. A little tricky, that one. That's pretty sensitive. So careful. Alright, then we got just one more here, which again pretty similar. There's a tangent, and I'll just leave this last one to you. You saw it takes a while. but I was set the middle equal to 0. Where am I starting? The period would be pi over 4, right? The period would be pi over 4. Maybe I could figure this one out right now. It's multiplied by a positive 4 too. The tangent's multiplied by a positive number, so it's going to be a rising curve between asymptotes. Well, let's see. This would be equal to 0 at just negative pi over 3. And the period's pi over 4. So I'd put negative pi over 3, negative 1. Let's see if I can move the black point to negative pi over 3. It's negative pi over 6, negative pi over 3, and then negative 1. And then move the asymptotes so that they're pi over 4 apart. Right, because the period is going to be pi over 4. Now, negative pi over 3 and pi over 4 have a common denominator, 12. This is negative 4 pi over 12. And if I go 3, that's 3 pi over 12. Now, a quarter, that would be pi over 16. Yeah. All right. Yeah, and I guess if I go pi over 8 to the right of this, so like 3 pi over 24, this is negative 8 pi over 24. If I move one of these asymptotes to negative 5 pi over 24, there we go. This works. Because what's the, see, negative 5 pi over 24, negative 11 pi over 24, and negative pi over 3 is exactly in the middle. The distance between these is 6 pi over 24, which is pi over 4 when you reduce, and that would be the period. I guess the only thing I need to change now is this blue point. Instead of, it would be it should have an output of 3 to get something with a tangent of 1 times 4 minus 1 would be 3. So I move this up so it has an output of 3. Looking like that there. I think this will be good. Again, I would recommend drawing. Great. There's a lot of mental math there, but I would recommend drawing it by hand first. Of course, drawing it by hand will make it a lot easier. Doing that key, the same steps I was showing you, the key value method every single time. Drawing one cycle and then possibly adding to that, drawing a second cycle, just so you get a picture where you have the tangent curve or cotangent curves, between two asymptotes. All right, so that's it for this section. Pretty decently long one, but it will be every time you're introduced to new graphs. All right, so now you've got the sine and cosine down, right? Y equals sine x, y equals cosine x. Remember, those are waves, just little wavy lines. And the period for sine and cosine, normally, the original sine and cosine was 2 pi. And now you have these tangent and cotangent curves, which are these rising curves or falling curves going all the way to the bottom, all the way to the top, between these asymptotes. And the periods of these, the plane tangent x, plane cotangent x, are 1 pi. All right, so if you keep those in mind, hopefully that'll make graphing these things a lot easier. All right, so hopefully this helps you, guides you through section 8.2 part 1. It's quite a bit, right? Quite a bit when you learn to graph these things by hand at first. And of course, if you have any questions, let me know. And thank you very much for watching.